So again, we're going to be going from chemistry and physics, thermodynamics, but don't be intimidated by that word because this is all related to stuff that we've already talked about. So if you are getting stuck with some of the concepts, try and relate them back to things that we've already covered, like enzymes and the reactions that they catalyze. So this is a little chart just reviewing different types of energy. And we are talking about potential energy and specifically chemical energy. And we'll also talk about thermal energy a little bit. Not necessarily as something we're interested in, but as something that is an unavoidable byproduct of some of the reactions that we're going to talk about, or a lot of the reactions that we're going to talk about. So when we're talking about chemical energy, what we're referring to is those chemical bonds that we've been talking about all semester. And different bonds have different stabilities. And the stabilities of the bonds relates to how much energy we say that they hold. And it's not really that they hold energy, it's that we're measuring the amount of energy of the system before and after the bond is broken, or before and after the bond is formed. So keep that in mind. We're not actually talking about, it's not like you break open a pixie stick and the dust comes out. You don't break a bond and energy comes out. It's looking at the system and the order and the disorder in the system. And we'll get into that in a moment. And I also wanted to remind us, just for the big picture, that in the cell, there's always kinetic energy and heat energy. So as we talked about, things are always moving around. We have vibrational energy of molecules. They're never staying still. And that's part of the reason why molecules come into contact. And then we also have heat energy, which again, we'll talk about more in a couple minutes. So to move forward in this conversation, we need to go over a little bit of vocabulary. And these are the two words that everybody always gets confused. What is entropy versus enthalpy? So does anybody know what entropy is? Claire?
The molecular disorder or randomness.
And then what is enthalpy? So if we said in the cell, there's a lot of kinetic energy, which has to do with disorder versus order. And then the other type of energy is heat. So, Michelle?
Is it whether heat is absorbed or released?
So it's just heat energy in general, yeah. So these are our two big components, are going to be entropy and enthalpy. So we're talking about heat and disorder. Or you might think of it as disorganization. I feel like that's a more kind of accessible concept. So we know that there are favorable versus unfavorable reactions. Talked about this a little bit. I'm sure you've heard of this sometime in the past. So what is a favorable reaction versus an unfavorable reaction? Well, Michelle just touched on it a little bit. So we could actually talk about this, favorable versus unfavorable, with respect to either of these two components. So we could talk about a reaction being favorable in terms of heat energy, or we could talk about it being favorable or unfavorable with respect to order versus disorder. And so keep this in mind. You're kind of balancing these two components when we're talking about these different types of reactions. Okay, so we're going to go to this video. And keep in mind, while we're watching this video, the question, when is something spontaneous? So we're going to actually watch most of this video because it's pretty informative. And make sure if you have questions, just jot them down and we'll talk about them after the video is done. And I might pause it. Also, this video shows a lot of equations. We don't need to know the equations. What we want to focus on are the definitions. And we'll talk more about what that means after the video, but don't get overwhelmed when you see these long equations.
If you write anything on your computer, you need to get Grammarly.
I write pretty much all day, every day, and Grammarly. Universe is chaos, whether it's the terrible state of my office or the slow degradation of my body into dust. The universe tends toward disorder. But why? Why is the universe structured in this terrible and callous way? Well, it turns out it's not really the universe's fault. If you think about it, there's only one way, or at best maybe a few ways, for things to be arranged in an organized way. But there are nearly infinite other ways for those same things to be arranged. Simple rules of probability dictate that it's much more likely for stuff, whether it's the stuff on my desk or the particles and energy that make up my concept of self, to be in one of the many disorganized states and in one of the few organized states. It's simple. It's unavoidable. So unavoidable that it is, in fact, our second law of thermodynamics, which says that any spontaneous process increases the disorder or randomness of the universe. Processes that don't increase the disorder of the universe require work to be done in opposition to the disorder, and are, in fact, often impossible to achieve. The very act of putting one system in order requires that other systems become disordered. Think of it this way. Your lunch was composed of an extremely ordered set of molecules, and it gave you the energy to clean up your house, maybe. And it had to be broken down into less ordered nutrient molecules for you to do that. Carbohydrates, proteins, and lipids, and those molecules were broken down even further as they were converted to energy in your cells. And then your body used some of that energy to power your muscles as you cleaned your house. But much of that energy was used to do things like keep your heart beating and breathe and make sweat. And some of that was lost to the surroundings in the form of random movement and, most importantly, heat. By the time you're finished, your house may be orderly, but the remains of your lunch molecules are all over the place. And that's only one of the many systems that became less orderly while you worked. So, yeah.
So I also wanted to just point out, this is one of the things that we were discussing a moment ago, that there are undesirable effects. There's wasted energy that is just a byproduct of biological processes because they're not 100% efficient. As we all know, we're not 100% efficient. That's okay. That's just the way it is. And so that would be the heat energy, the sweat, and things like that.
Cleaning your house, in fact, increased the overall disorder of the universe. Next time someone gives you a hard time about the state of your house, you can tell them that. Obviously, disorder is a pretty big deal in the universe, and that makes it a pretty big deal in chemistry. So scientists have a special name for it: entropy. Entropy is a measure of molecular randomness or disorder, and even though people complain about the disorder in their lives, it's not all bad news. Entropy helps make chemical reactions possible, and it helps us predict how much useful work can be extracted from a reaction. We all have to live with disorder, so you might as well understand it. For the next 10 minutes, I want you to embrace the chaos. So what does the second law of thermodynamics mean when it says any spontaneous process increases the disorder of the universe? Spontaneous simply means a process that doesn't need outside energy to keep it going. And it goes the other way too. Anything that increases the disorder of the universe happens spontaneously. That doesn't mean disorderly things will always happen, though. Other factors may interfere. The reaction to change a diamond into graphite, for example, would be thermodynamically spontaneous. It wouldn't have to be forced along by outside energy. But the bonds in the diamond are so stable that essentially it never gets started. Lots of other chemical reactions are like this too. So even though we sometimes think of spontaneous as meaning sudden and impulsive, like the majority of mall lit piercings. In chemistry, spontaneous doesn't tell you how quickly something happens. It only means a reaction is thermodynamically capable of happening without outside energy to move it along. Though come to think of it, I imagine that spontaneous slip piercings cause a fair amount of disorder as well, especially upon arriving home. Entropy is another state function. It doesn't depend on the pathway the system took to reach its current state. So even though we can't measure the entropy of reactants or products directly, we can calculate them. We can also calculate the change in entropy that occurs during a reaction, exactly like we can for the change in enthalpy, by subtracting the sum of the reactant values from the sum of the product values. In other words, the formulas look exactly the same, just substituting S, which for some reason is used to denote entropy, for delta HF. Notice that we dropped the deltas on the right side of the formula because we know absolute values for entropy of individual reactants and products. We keep the delta on the left because we're calculating the change in entropy that occurs when the reactants rearrange into products. What the heck is this good for? Well, we can explain a mysterious thing, which is how reactions occur spontaneously in nature even though there's no energy given off, or even they suck heat out of the environment and seem to go up the energy ladder instead of down. Let's try it out with a real reaction here on my desk. This is one of my favorites. This is barium hydroxide octahydrate, and this is ammonium chloride. Usually, we do chemical reactions in aqueous solution because most solids don't interact easily, but this pair is an exception to that rule. They react readily in solid form, and this reaction absorbs a lot of heat from the surroundings, making everything around it feel cold. Now, to show you how cold it gets, I'm going to do something here. You're just going to have to assume you understand what I'm doing. What am I doing? What is happening? Why am I doing this? That's weird, Hank. Why are you doing that? And I'm going to put that on there. So I've got my barium hydroxide in this beaker. Now I'm going to dump the ammonium chloride in. And now one of the byproducts of this reaction is ammonia. So I'm going to have to smell that, but you don't. Oh yeah, look at that slush. I think we've reacted pretty much completely here. And so we should, if all things have gone properly, yep. That's pretty cool. Sucked enough heat out of the block of wood to actually freeze it to the beaker. In the world of chemistry, a reaction that proceeds spontaneously and yet absorbs heat is really weird. Basically, I have a hard time believing what I just did. So what does entropy have to do with this little freak show? You might think it has something to do with taking the heat from the surroundings to make the system colder. While that's counterintuitive and cool, that's not all of it. You might also think that it has to do with two solids combining to form a whole bunch more liquids and gases, and that is a big part, but still not all. To understand what we just saw a little better, we need to put it all together. Let's start by finding out exactly how much heat it did absorb and what happened to the entropy as well. First, we'll find the enthalpy change using Hess's law and standard enthalpies of formation. We can use the coefficients from the balanced chemical equation to fill in the number of moles for each substance. Then we have to look up a whole bunch of numbers. Remember, you can find tables like this online and probably in the back of your chemistry textbook too. When we plug the standard enthalpies of formation into the formula and do the math, we find that the change in standard enthalpy is plus 166 kilojoules. It's positive, which makes sense because the reaction absorbed the thermal energy. Enough to create about a half a kilogram of ice if it had been surrounded by water instead of air and fingers. Next, we'll find the entropy change. Remember, the basic equation is the same. We put in the number of moles from the balanced chemical equation and the standard entropies from the table, and a quick calculation tells us that the change in standard entropy is 594 joules per Kelvin. A positive result means the entropy of the reaction increased, meaning the products were more disordered than the reactants. Note that the standard enthalpy is in kilojoules while the standard entropy is in joules per Kelvin. The energy units should match, so let's call the standard entropy 0.594 kilojoules per Kelvin. It doesn't look like much right now, but wait, there's more. Those numbers don't explain why the reaction proceeds spontaneously even though it scavenges all that heat from the environment. But Josiah Willard Gibbs, he found a way to explain it, and he didn't even mean to. Gibbs was interested in the amount of energy in a system that was available or free to do useful work. Today, we call this Gibbs free energy, or sometimes the standard free energy, or simply free energy of the system. Like enthalpy and entropy, Gibbs free energy is a state function, so it can be calculated the same way. We simply substitute delta G, which stands for Gibbs free energy, for delta H or S. The standard free energy of formation, written like this, the change of free energy that occurs when
when a substance is formed from its elements in a standard state. It's analogous to the standard enthalpy of formation that we use to calculate change in enthalpy. Like enthalpy and entropy, we can't directly measure the free energy change of a whole reaction. So scientists created a baseline by setting the standard free energy change of formation for an element in its most stable form at standard state to 0. The standard free energy change of formation for a compound, then, is just the difference between its standard free energy and that baseline. But what if you don't know the standard free energies of formation for the products and reactants? Well, they're often listed in tables, but sometimes the ones you need aren't available. Never fear, Willard Gibbs has an app for that. It's actually a formula, but he figured it out. In 1873, Gibbs calculated that at constant pressure and temperature, the change in standard Gibbs free energy for a reaction equals the change in standard enthalpy minus the product of the temperature and the change in standard entropy. In other words, the amount of free energy a reaction makes available to do work depends on two and only two things: the enthalpy change, the amount of heat the reaction transfers, and the entropy change, the amount of disorder it creates at a given temperature. So which is more important, the heat transfer or the disorder? Well, it depends. A large change in enthalpy can determine the direction of a free energy change, even if the entropy changes in the opposite direction and vice versa. If the absolute value of the change in enthalpy is greater than the absolute value of the product of the temperature and the change in entropy, or T delta S, then we say that the reaction is enthalpy driven. This means that the flow of thermal energy provides most of the free energy in the reaction. On the other hand, if the absolute value of T delta S is greater than the absolute value of the enthalpy change, we call the reaction meaning increased disorder provides most of the reaction's free energy. Which type was the barium hydroxide reaction? Well, I'm gonna say that the temperature in here is about 25 degrees Celsius, or 298.15 Kelvin, because I'm awesome like that, I can just tell. When we multiply that by the change in entropy that we calculated, 0.594 kilojoules per Kelvin, we get a value of 177 kilojoules. If we compare that to the change in enthalpy we calculated, 166 kilojoules, it is clear that the T delta S is higher than the delta H. So the reaction is entropy driven, no surprise there. Even though the reaction absorbed a lot of thermal energy, this phenomenon was dwarfed by the increase in entropy. And this makes sense because the balanced equation goes from 3 total moles of solids with their molecules locked in place to 1 mole of solid, 10 moles of liquid, and 2 moles of gas. This is a massive increase in disorder because in addition to the fact that there are now 13 moles of particles to move around instead of just 3, the liquid and gas are particularly good at moving around, so most of those particles are in random motion, no longer stuck in one spot, causing a large increase in disorder or entropy. But here's the coolest part: Gibbs' formula also tells us whether the reaction is spontaneous or not. We know all systems tend toward the lowest possible energy state, whether it's a ball rolling down a hill, elastic springing back into shape, or positive and negative ions forming a bond. Delta G is a type of energy, obviously, so it spontaneously approaches the minimum possible level. So if the value for delta G is negative, that is, if the free energy decreases, the reaction is spontaneous. Reactions that are able to release free energy don't need external energy to make them proceed, and that's the very definition of a spontaneous reaction. So if delta G is positive, the reaction is non-spontaneous, but the reverse reaction is spontaneous. If delta G is 0, the reaction is in an equilibrium state and no discernible change occurs in either direction. So what about the reaction I just did? Is it spontaneous at room temperature? Can it occur without energy driving it along? Well, yes, because we just watched it happen. But let's do the math. Using Gibbs' formula and plugging in the numbers that we've calculated so far, we see that the Gibbs free energy for this reaction is negative 11 kilojoules. It is indeed spontaneous because it releases energy instead of requiring it in order to get started. The energy that was produced was used to rearrange the bonds and the reactants, to make smaller product molecules, to break attractions between molecules, and to push some of the particles apart from solid form into liquid and gas form, which increased the entropy of the system. So even though the reaction absorbed a lot of thermal energy, it didn't need that energy to make it proceed because the large change in entropy alone was enough to keep things moving along. So Gibbs' formula confirms our earlier results with just one little subtraction. Pretty smart guy. And now, some of his smartness has been transferred into you. Now that you've watched this episode of Crash Course Chemistry, if you paid any attention, you learned that it's hard to stay organized because there are so many ways to be disorganized, that the second law of thermodynamics says disorder or entropy happens everywhere, and that the change in entropy ultimately depends on how much room molecules have to move around and how much heat energy they have to give off in reactions and the temperature around them. You learned about Josiah Willard.
Okay, so that was a lot of stuff, but we're going to review some of that, and the link is right here. So you're welcome to go back and watch that again. But watch it slowed down, which I know some people do. You can watch it sped up too. I don't know why you would do that, but you could. So he talked a lot about disorder and touched on some pretty good points. So what do we mean by disorder?
It's 10 o'clock.
It's 10 o'clock. So when we're talking about entropy, just did a little doodle here to help us remember. When we're talking about disorder, what is more disordered in terms of some molecules? Well, gases tend to be more disordered than liquids, and liquids are more disordered than solids. So if we see a reaction that's making liquids from solids, or if we're going to gas, then that's going to increase disorder. The other thing that he touched on in the video was that smaller molecules have less order, they're more disordered. So if you think about the diamond or any kind of network or lattice, so here's a good one. We talked about ice in the beginning of the semester. So ice was kind of like a cross-hatching of water molecules. They're all positioned a certain distance away from one another. They're all oriented in a certain direction. If you melt that ice into water, then the molecules have much more disorder because they can move around, they could spin, they can get closer or further from one another. And so instead of having one large network, you have a lot of smaller molecules that still have some influence on each other in that they form what types of bonds? Water molecules, hydrogen bonds, but they are not very strong bonds, and they're not holding them steady in place. And we already know what the difference is when we're talking about using heat versus releasing heat. And another reaction, similar to what Hank did there, is if you make instant pudding. So who's made instant pudding? Like with the powder and the milk. And then once you stir it, you notice it actually gets cold because that reaction is using some heat energy to make the reaction go forward. So that's another good example. So as I said, we don't need to know all those formulas that he was doing, but I do want you to know the different components of this. Again, the disorder and the temperature and how one or the other can drive a reaction. And you should know what the Gibbs free energy constant is, which is the delta G. And we'll talk more about a positive value for delta G and what that means versus a negative value. But I just wanted to mention here that we can also have 0, which is at equilibrium, but mainly we're going to be talking about values greater than 0 or less than 0. All right, so this is another good example, everyday life, of a reaction that is unfavorable. So in this reaction, she is building up this card pyramid, and she's really decreasing the disorder. So this reaction is unfavorable. It's significantly decreasing the disorder in this system. So this reaction would have a positive delta G. We would expect it to, because it has lower entropy at the end. If we look at what happens in the next few moments, as we might expect, the opposite reaction, which is the pyramid falling apart, is going to disorder. And again, that's because there's less structure to how the cards are arranged with respect to one another. There's different orientations for the cards, and overall it's becoming less ordered, less structured. And this reaction we expect to have a negative delta G. So at room temperature, only highly unstable molecules are going to degrade spontaneously. So there is still this reaction between, or this relationship between order and disorder and temperature. So that's why our biological molecules, even though they have a lot of order, they don't spontaneously fall apart. They're stable enough, and there are other disordered elements to the system that our biological molecules could hold their structure. Our DNA is very highly ordered. Our proteins are very highly ordered as well, and they're stable at room temperature. We have talked about, however, when we heat up DNA or we heat up proteins, what happens? Do they hold their structure? So DNA falls apart, the two strands, the hydrogen bonds melt, and proteins denature, which means that they lose their shape. And there are different variations on what would happen. But yeah, they're not going to be as ordered. And as you up the heat more and more at very high temperatures that we haven't discussed, you could even melt off the nucleotides or the amino acids eventually and break those bonds as well. So that would increase disorder even more. But in general, those kinds of reactions need a lot of heat input in order for them to go forward. So again, we're balancing that disorder and the heat component. So the question that I always ask with this is, if we had this hard pyramid at 0 degrees Kelvin in a vacuum in outer space or something, well, I guess not in outer space, but in a vacuum, would it still fall down? Why? Okay. Any other suggestions? So if we have the same hard pyramid without any gas around it, it's in isolated space, and there's also no heat energy in that space, in that box, what would happen? Would it stay together or would it fall down? Yep. Okay, so Michelle and Joanna say let's stay together. Riley says it's going to fall apart.
No,
Oh, you said it would stay together. Okay. So does anybody think that it would fall apart? No? Unpopular opinion? Okay. I don't have an answer to this, but I think that you could argue it either way. So I'm just trying to get you to think about what the components of the system are. I think that there is an argument that it would fall apart because that would decrease the order of the system. It would increase disorder. But I don't know if you'd be able to overcome the activation energy, which is the energy needed to start a reaction, which we'll talk about in a couple of minutes. So I think those were good answers, suggestions. So going back into molecular biology, as I said, we've talked about reactions before. We've talked about formation of molecules and degradation of molecules, and they are stable, but some molecules we've said are more stable than others. Or another way to say it is that there's more energy in the bonds of certain molecules. And again, it's in the bonds, it's not actually in the bonds, but the really technical reasons for this are here. So we have this molecule, this is ATP, and we've looked at kind of related molecules. We've also talked about GTP, so the same thing would go for that. And we have the nucleotide part, and then we have the 3-phosphate part. And so what did we say about these 3 phosphates? They don't like to be next to each other, these phosphate groups. And why was that? Does anyone remember? What do we see a lot of? Negatives, yes. So there are a lot of negative charges on these phosphate groups because of these oxygens. So these oxygens, these two, this one and this one, the negatives repel one another. So that's the unstable part of this molecule. So we can make a more stable set of molecules and increase disorder by breaking this into 2 molecules by removing one of the phosphate groups. So now we have ADP plus an inorganic phosphate. We have fewer negative charges on the ADP that are repelling each other. And in addition, I think that we talked about in the ADP, we actually have lots of magnesium in the cell. So magnesium has a 2+ charge as an ion, and so that could actually interact with the 2 phosphates on the ADP. So it could stabilize that pretty well. So there's like a bonus. In addition to there being fewer negative charges overall, then there's this added stability of magnesium being able to stabilize these 2, but magnesium can't stabilize all 3 of the phosphates. So down here, once we break off that phosphate group, we have a more disordered system, a more stable system. And so we say that we go from high energy to low energy. So again, breaking that bond doesn't actually release energy out of the bond, but we go from a higher energy state to a lower energy state. And where does the difference in energy go? Well, we often use it to power enzymes, make reactions go forward, or do other things, so break or make other bonds. And we see that the value for the Gibbs free energy here is going to be less than 0. It's going to be negative. So this is a favorable reaction, as we would expect from things that we've learned in the past. Going from ATP to ADP is a favorable reaction, which releases energy. The opposite reaction, making ATP from ADP, which we'll be talking about in photosynthesis and cellular respiration, this reaction is not favorable. So we're putting that phosphate group onto the ADP molecule, making a more unstable molecule. We're increasing order and decreasing disorder. So this takes energy. So our Gibbs free energy constant here is going to be negative or positive? Positive, right. We're going to have a positive value for this reaction that's going to need energy in order to go forward. And as he pointed out in the video, you could find this type of information in your textbook, in your chemistry books, on the internet. We're not going to be dealing too much with the numbers, but I want you to kind of get a sense of the values that we're looking at. So in the cell, we're looking at kilojoules per mole, and we're seeing these relatively low values. So for this highly favorable reaction that we see a lot in the cell, ATP plus water, being broken down into ADP plus inorganic phosphate and hydrogens. This is going to release about 32 kilojoules per mole of energy. And we see that you could also do this reaction. So we've talked about this, I think, once, referring to DNA polymerase. So if we take two of the phosphate groups off of ATP and end up with AMP that is monophosphate, and we have two phosphate groups off and bound to one another, then we release even more energy, but we don't see that as often as just breaking off the one phosphate group. So what is the delta G, or Gibbs free energy, affected by? Well, stability and the bond energy of both the products and the reactants, the temperature of the surrounding environment, and also catalysts. So catalysts are things that make a reaction go forward. So even if a reaction is favorable, as we've said, it doesn't mean it's going to spontaneously go forward, because we have lots of ATP in our cells. It doesn't just spontaneously fall apart. That would be really bad, because we, quote unquote, store energy in ATP. It's the currency of the cell. If we just had dollars that spontaneously fell apart into pennies, that would be really bad, right? That's not what we want. I guess that analogy isn't technically correct, but that's okay. So in reality, many reactions in the cell look something like this. So we have reactants on one side, and then we have products on the right side. And then this is sometimes filled in, or sometimes we could draw it as a line. And this is showing the total energy of all of the molecules pertaining to this reaction. And this would show a favorable reaction. So something like ATP being combined with water and being broken down into ADP, and the inorganic phosphate and hydrogen. So we know that ATP is higher energy, has more order. So we want to go to the product, which is ADP and inorganic phosphate, which has more disorder. But it doesn't just degrade. And that is because of what's called the activation energy. Sometimes this is referred to as an energy barrier. And this is what proteins or enzymes in particular usually help to lower. And let me acknowledge the fact that if you had a literal box full of ATP and kept it for 1,000 years, yes, some of the ATP would break down into ADP spontaneously. But it would break down much faster if you threw in an enzyme like DNA polymerase, or another enzyme that could use that ATP and break it down into ADP, as long as the other components of the reaction were in there. And we'll see an example of this in a couple of minutes. So what an enzyme does is that it doesn't necessarily get rid of that space between A and B completely, but it decreases it a lot. So A was somewhere up here, and now we only have to overcome this activation energy. It's much lower in order to break down ATP into ADP. And again, the reason for this is because of the enzyme. Now, does anyone know how we actually decrease this activation energy? And this is kind of a tricky question. This is an advanced question for our class. So talk to the person next to you for 30 seconds or a minute, and we'll see what ideas we come up with. I'm sure this was in your reading somewhere. Okay. Again, how does the enzyme reduce the activation energy physically. So talk to the people next to you, 30 seconds.
This is in the PCR lecture reading?
No, this is your textbook. Did I have a suggestion in the back? Yeah?
Is that one?
Ooh, so an inhibitor is kind of the next layer of complexity. But you could think of it in kind of a similar way. What is preventing these molecules from interacting and degrading? Does anyone else have any ideas? Yeah.
The enzyme has the specific shape that fits the reactant and it binds to it, so it doesn't degrade.
So the enzyme binds to the reactant, has a specific shape, which we've been talking about in the beginning of the class, right? Enzymes fit specific molecules. And for this reaction in particular, an enzyme has a binding site where it could bind ATP, and it also has a binding site where it could bind water. So it's going to bind both of the reactants. And they're now both in the enzyme, and they're close to one another. Not only are they close to one another, but the enzyme is putting the particular atoms near each other that need to react. So a minute ago I said we could have this box full of ATP. Is it going to degrade ATP and water? Well, you would have to have a random movement of the ATP in the water generating the molecules coming into contact and the exact atoms coming into contact to break bonds and form new bonds. Instead of letting that happen randomly, an enzyme can bind both of them and kind of put them really close together and say, okay, are you guys going to react? And the actual breaking of bonds and making of bonds is still spontaneous. It has a little bit of probability, but you're making it so much more likely to occur because you're orienting them correctly with respect to one another. So that is basically the main thing that enzymes do. And there's a bunch of chemistry that we can talk about, but overall, that's what they're doing to decrease this activation energy. They're putting molecules near each other in the right place. And then we get the products forming. Yeah?
And there's another way that, I read that if they can stretch the substrate molecules for the transition state and like stress and shrink the bonds.
Right. So part of the putting them in the correct orientation is not just putting them in the right orientation with respect to one another, but it can also be things like stabilizing charges and also stretching bonds. So literally pulling apart atoms that are in the same molecule to kind of encourage them to interact with other atoms to break those bonds. Again, this is kind of an abstract concept, and that's okay, because we're not a biochemistry class, but I want to give you some background as to, why all this stuff is happening. It's not magic, it kind of seems like magic, but these particular things that we know something about are happening within this protein. So it's not totally a black box. And this is how enzymes reduce that activation energy so that things don't just happen randomly. It's not a very low chance. We're increasing the chance a lot. So I have a couple of analogies with this. And my first analogy is dancing at a wedding. So how many of us have been to a wedding at some point in our lives? Most of us. You have. So a lot of times the dance floor is empty at the beginning of the wedding, once the speeches are being made and whatever. Because it's really awkward to be the first person or the first couple is going to dance on that empty floor, right? So this would be the transition state, like the first person or the first few people. And there are transition states and molecules too, which we'll talk about in a minute. And I always refer to transition states as like awkward time because it's high energy and it's unfavorable. So the solution that we use at weddings and other social situations is music, drinks, and food. And this makes people get out on the floor, right? What else has really changed? It's just that we've added these catalysts that encourage people to dance. And then after you get those first few people out on the floor because they were the first ones to eat and drink, and maybe their favorite song was playing, then you get lots more people out on the floor, right? Same thing with school dances and whatever else. And so again, that transition state is really important because without the food, drinks, and music, then that first person to go out on the floor, it's going to be a lot harder to get them out there, right? My husband had a very specific formula for how much he needed to drink before our first dance at our wedding. So another analogy here, which you might also be familiar with, is clipping the nails of your cat or dog. This is a joy if you're a pet owner. And here our enzyme is a towel. So here we really get the idea of the enzyme being something that positions things correctly. So here in the towel, you're wrapping up this cat. This cat is obviously drugged because he's not friendly at all. But you see that you're physically arranging the cat so that you can clip the nails more easily. You're keeping the head and the teeth away from you so you're not getting bit. And so it again helps lower that energy, that high energy of the transition state, which would just be starting to clip the cat's nails. And so this makes it a little bit easier. So this is what I was referring to earlier, or kind of what I was referring to earlier. And this shows golf balls, a little bit more abstract. I apologize. So this is a bunch of golf balls in a box, and we're just pretending that they have some reaction that turns them brown for some reason over time. So if you wait a year, the speed of the reaction, if it's happening without any kind of catalyst, you just get this amount of golf balls turning brown. So a small fraction of them are going through this reaction randomly, just like we were talking about with the box full of ATP. If we add some kind of enzyme or catalyst that increases the probability of that reaction, then we have all of them turning brown in 1 second. And this is the real difference between reactions rates with and without an enzyme. So this nifty little chart here shows the comparison between uncatalyzed reactions, so again, happening just without any help, versus catalyzed reactions. And so this enzyme here, OMP decarboxylase, which is an enzyme that is in your body that does certain metabolic reactions. If we didn't have that enzyme, then yeah, that reaction would go forward and occur once every 10 million years, which is not fast enough for us to survive on. But this, the reaction that this enzyme catalyzes occurs multiple times a second in our bodies because of this enzyme. And this is actually a relatively slow enzyme. This is the slowest one on this chart. So life would really not be possible without enzymes. In particular, most of the time we're talking about proteins when we say enzyme. What's the other type of enzyme that we talked about last week, 2 weeks ago? Yeah? Ribozymes, right. I bet I could see a lot of people were thinking that and they were like, no, that's wrong. But yes, there are also some enzymes that are made up of RNA, And we talked briefly about how there's the possibility that RNA was the first molecule on Earth. And now we kind of see the importance of that, right? Because if the first life was made up of RNA, and this RNA was a ribozyme, then all of a sudden we can make some reactions go forward hundreds, thousands, millions of times faster than they would have previously. So this was probably a point in the history of life where things started to speed up a lot. If at first we were unable to control reactions and we needed to depend on them happening spontaneously or randomly, and then we got enzymes, even if they were inefficient, they're much better than just relying on chance. Okay, so this is our model of enzyme-substrate interactions. So we've probably all seen something like this before, and this does a really nice job. Here we have the enzyme, and here we have the substrate, which is clearly going to be broken into two different shapes. And we see when the enzyme binds the substrate, this is illustrating that it's stretching the bonds, as Claire pointed out. So it's not only orienting the circle and the square correctly, but it's also stretching the bond between them. What else do we notice in this middle image? The enzyme is not the same as it was when it's unbound to the molecules, right? And so this is our modern understanding of what happens. The enzyme, or the protein, changes shape, has what we call a conformational change. So again, that's a conformational change when the enzyme binds to the substrate or the reactants. And that's really important because it allows the enzyme to respond to the substrate. And as I tried to illustrate here, the active sites of the enzyme are not a 100% kind of complementary match to the substrate. If they were 100% complementary, then you wouldn't have this space here, right? You just have the circle and then this notch right next to one another. So the enzyme has to change shape a little, and that encourages the substrate to change shape as well. So this is our modern understanding. It's called the induced fit model. You have probably heard of the lock and key model before. This is still, I think, a good model to think about because it illustrates how, or why rather, an enzyme is not going to bind to different molecules and catalyze reactions. So we said, for example, that antibiotics target what bacterial molecule? Antibiotics will bind to the bacterial ribosome. And we said that they don't bind to human ribosomes because human ribosomes have a different shape. And so that has to do with the different shapes of the active sites. And that's why the antibiotic only affects the bacterial ribosome. And so that's what this lock and key model really emphasizes. And when this model was developed, scientists didn't know that the enzyme actually changed shape. So they thought the enzyme just stayed the same. Now we know that it changes shape, and that really illustrates well the transition state when we start to stretch the bonds and stabilize certain parts of the molecule. And that's really important for understanding why we have activation energy and how it's reduced by the enzyme itself. Okay, so we can graph the action of enzymes in a couple couple of different ways. Whenever we are just looking at an enzyme, the concentration of an enzyme, and on the y-axis, the velocity or the rate of reaction, as you add more enzyme, the rate of reaction increases. So if we go back to our box of ATP and water, if we put an enzyme in there, just 1 mole of enzyme, then the reaction is going to go forward. But if we put in 2 moles of enzyme, then the reaction is going to go forward much faster. So that's all this graph is showing here. But this is assuming that we have optimal conditions for this enzyme to work. And so here we have the rate of reaction on the y-axis again, but then on the x-axis we have different temperatures and then different pHs. And at different temperatures and different pHs, you're going to have a protein losing its shape. And so that affects its efficiency, its ability to bind the substrate and do its job, essentially. So this is the optimal temperature for a typical human enzyme. So we see it's right around what temperature? It's around body temperature, so around 37 degrees Celsius. So it's optimal temperature for our enzymes. They've evolved to operate under this temperature because they've evolved inside of our bodies. Whereas this is the optimal temperature for a bacterial enzyme that lives in hot springs. Okay, so the temperature, optimal temperature, is completely different for these bacteria because they evolved in hot springs. So this tells us a couple of things that, first of all, you can have enzymes working slowly at temperatures that are usually lower than their optimal temperature. If you bring enzymes higher than their optimal temperature, then their efficiency drops off really fast because they start to denature. And it also shows that we have enzymes that reflect kind of their evolutionary history in that they work best in the environment they came from. So for those of you who completed the PCR assignment, the enzyme used for PCR is called Taq polymerase. Does anyone remember where that came from? So it's a bacterial enzyme, and it came from a species called Thermus aquaticus. So right there you get an idea that it came from somewhere warm. This was actually a bacterium that lived in a hot spring. So when we do PCR, it's really nice because if we did PCR with a human enzyme, if we were doing our reactions and setting it up, when we put in the enzyme and it was about room temperature, somewhere around here, then we would start the reaction working even before we were really ready for that, before we had all the components in it, right? Instead, we use something, the Taq, which looks more like this in terms of its energy, its enzyme activity. And so if we have this at room temperature, or usually we even do it on ice, we're not going to have any reactions before we're ready for that reaction to really start. We have all the components together. So it's really nice we can control that because that enzyme is just too cold to start performing its reactions. And so we see something similar for the range of pHs, and in this we have 2 human enzymes, but they're from different parts of the body. So one is in the stomach, and then one is, I believe this is in the intestines, but it might be just in other parts of your body. Obviously, The stomach has a different pH than most other tissues in your body, and this enzyme works best at the pH of your stomach. And if you take it out of your stomach, then it's not going to work correctly. And so this is another reason why we really need to keep enzymes in particular conditions if we're going to use them in the lab. So I will end with, so this might be an example of something that we could put on the door for Halloween, because this is kind of creepy. So I brought up a couple of connections to the skincare universe before. So has anybody used pineapple extract in skincare? I know there are a couple of things. I think that it was more popular a couple of years ago. But if you see pineapple extract, it's useful for exfoliation because pineapple actually has a bunch of, or a protein rather, that can break up a bunch of different proteins. So normally we see some specificity, a lot of specificity in protein and enzyme, and then what other proteins it can break down, right? Because of those active sites. But this fruit protease, which comes from pineapples, can break down lots of different proteins. And so this in the pineapple is used to get pineapple ripe really quickly, because this one enzyme could take all the different proteins that were for growing the pineapple and break them down and say, okay, we're a mature pineapple now. But potentially, I guess, we could use this enzyme for exfoliation because it has a really broad set of molecules that bind to and break down proteins. It's also been proposed as an anti-cancer agent because, again, it could just break down a lot of proteins, potentially do some damage on those to those cancer cells. Okay, so later in the week, we're going to get into photosynthesis, and that will be our lab for this Friday. Remember, you can sign up for office hours for Wednesday in the back there. You can bring in a picture for the door. What else did I remind everyone about? You could email me about lab reports. Claire, was there a question?
I just wanted to ask about like an analogy. So say you're going up a hill. So you at first need the energy to get you to the top of the hill, right? So that
Yes.
would be the activation of it, right?
Yes.
Okay, and then you release the energy as you're going down the hill.
Yep.
So then would that mean that delta G would be 0?
So delta G is calculated by using the reactants and the product values. So the activation energy, we don't pay attention to.
Okay.
Yeah, it's a good question. Any other questions, suggestions, freakouts? No, okay. Excellent. I am working on your exams. They look good so far, but I have not finished grading them. So look forward to those towards the end of the week. What day were we going to meet?
Wait, I asked you the time on Friday, but I don't know if
Right.
you got
Okay. I don't think that I got back to you.